Okay, then click your segment tool and create any size segment you want. We want to create the perpendicular bisector of that segment. All right, so there is one and only one line that is perpendicular to that goes through the midpoint of that, right? Okay. What's nice about GeoGebra, and I don't want us to do this, but if I click on this tool here, this fourth option, I can go down to click perpendicular bisector, and then click the line that I want to do the perpendicular bisector for, and it automatically puts it in. Okay? So maybe you want to do that real quick, just to get a visual of what we're going to come up with, and when we're done, see if we get that line. But what I want you to understand is that we're going to do the work that GeoGebra is kind of doing instantaneously for us when we choose that option. Okay? So hit Control. If you've done that, then hit Control Z just to get that out of there. But that's what we're going to come up with. And it's actually a pretty easy process to come up with that segment or that line, but it might be a little bit more difficult to prove why that is true, why it works. What I want to do is I want to come up to my circle tool, and let's go down to circle with center and radius. Okay. This option, this tool, is most similar to having a physical compass in my hand, to where I could, adjust the legs of that compass and make it 5 inches long, or 6 inches long, or 3 units long, or whatever. Okay. I want to click on A, and it's going to ask me for the radius, right? The only thing that you have to worry about here is that we want a radius that is bigger than half your segment. Okay? There's really no limit to it in regards to how big it could become. Kind of be intelligent about it. But we want a radius that is bigger than half of my segment. So you're seeing your segment over here being, mine's 11.2. So I'm going to, half that's, 5 something, right? 5.6. Okay. So I'm going to make a radius that's 6 or bigger. Okay. So I'm going to go 7. So yours is going to be maybe different than mine. I'm just going to use a radius of 7. Hit OK. Puts in a circle around A, right? Okay. You're going to then go to point B and do the exact same thing. The exact same radius. Okay. Hit OK. And those two circles should intersect, right? Okay. Now, when we're drawing these circles, and a lot of times when you use congruent circles, the goal or the reason we're using congruent circles is because we want the intersection. Okay. So let's come up to our point tool, go down to intersect, and then we'll click on our two circles. You can click on them over here in the plane, or you can actually just click on the names over here, and it'll show me the intersections of C and D. Okay, is that all right with everybody? We need those to exist. We need those intersection points to exist. That's why we had to make our radiuses larger than half. Okay. For instance, let me go back. If I would make my radii 4, see how those do not intersect? So then I don't have those points that I'm going to need here in a moment. Okay. So we need to at least be bigger than half the original segment. I think I can. Here's another thing. I didn't know this existed, but I can do this. If I say I create my circle here, it was 4 units long for the radius. If I double click on that, it gives me this information. What do you think that 4 represents? The radius. So if I don't want it to be 4, but I want it to be 7, I could edit that, hit apply, and it makes it 7, right? So those are options for you. You can do the same thing over here. Click on that, make it go to 7, hit apply, and I'm good to go. So we wanted those intersection points. So you guys' probably looks like that, right? How many points do you need for a line? How many points needed for a line? 2. Okay. Do we have 2 points right now, C and D? Take your line tool. You can use a segment or a line. I'm going to use a line. And click on C, and then click on D. And what have we created? The perpendicular bisector of AB. Does that make sense, everybody? Those steps? Not really hard steps, right? If we break down, we talked about it a lot, but if we break it down, we put a circle around A, and we put a circle around B, and they were congruent circles. They had to be the same size. And then where they intersect provides you 2 points that will end up bisecting this segment, okay? And if you don't believe me that it bisects that segment, we can do some work here. We can ask for the intersect option. Click on the line tool. Now click the one that says line. And now click on C and D. There you go. Let's find the intersection of these two things. Let's find A, B in segment CD or line CD's intersection. So I'm going to click on the line and the segment. And it should give me point E, right? And you guys got options. You got different ways that you can find that point E. But the reason I wanted to do that is because now let's find the distance. Let's find, come over here to your angle tool. This is your measurement tool, but it's defaulted as the angle. Come down to distance or length. And now here it says select 2 points, a segment, polygon, or a circle. Okay? We want to find the length of a segment, so let's click on 2 points of the segment. Let's click on A, and then click on E. And it gives me 5.6, right? If I click on then E, and then B, it's 5.6. Okay? Does that convince you that that is a midpoint, that E is a midpoint? Okay? You can kind of maybe jockey these points around a little bit. If you want to move A, move A. But what's nice is that that perpendicular bisector stays in there, right? Now, eventually, and then the relationship between these two distances stays the same no matter where A and B go. But eventually, things kind of blow up, don't they? And my perpendicular bisector disappeared. Does anybody want to know or guess why it disappeared? What was the first step? What was the first criteria that we had to have about our circles? They had to be bigger than what? Half of AB, right? Half of AB right now would be a little bit bigger than 7, correct? If you remember, my radius was 7. So if I highlight my circles, they don't intersect. And that's why when I move A and B around, things disappear. Okay? Because the construction is not valid. It's what we call an undefined construction right now because they're not intersecting. But the moment, now there, those two circles are said to be tangent to one another. They intersect one another one time. And in this case, it's going to be at the midpoint, but it's really difficult to visually see that they're intersecting because if I zoom in, we see that they're really not intersecting. So I don't want to have to do it that way. So the goal is to make our circles intersect at 2 spots, okay? And then we start to see that line can be created. And we have those 2 points that determine a line. Okay. All right. I want to walk through why this works, why this is true. If you click on distances or whatever and it shows up as a text, you can hide text as well. Okay, so I just get rid of that stuff. I want to, you guys can just watch this. You don't have to do this on your own. I'm going to create a couple segments here. I'm going to make my picture here Yeah, kind of like that, just to eliminate any potential confusion. I'm going to create a segment AC and AD. All right, if I create those two segments, AC and AD, and I bring back in that circle right there, what are those two segments for that circle? Radii, correct? They're both an individual radius of the circle. So what do you know about those two red distances? They're the same, right? Compare them to one another, they're congruent. So keep that in mind. What if I come over here and look at C to B and then D to B? What are those things for that circle? Radii. And what are they? The same, right? They're congruent to one another. Do you remember what we said about those two circles? What was the dimension of those two circles? What was the one value that we used to create those circles? The radius, right? And we said that the radius when we created both those circles had to be the same, correct? So what's that tell you about both red lines compared to both blue lines? They're the same. Okay? So we've got these four lines here. When I connect those four lines are all congruent. Okay? So let me do this. It's actually, that was stupid. We're going to just change them all to red. And I'm going to put that information in there. Okay? So we're trying to prove why we know for certain that this line here is the perpendicular bisector of AB. If I look at that triangle right there, what kind of triangle is that? I heard it. Somebody say it. Is that isosceles? You hear that? Okay. Would you agree that that triangle there is also isosceles? Okay. Would you agree that the maroon triangle at the bottom and the white triangle on top are congruent? Side, side, side? So you have two congruent isosceles triangles, right? What is a nice feature about isosceles triangles in regards to maybe the angle here, where my cursor is, and this angle over here? What do you know about those two angles? They're congruent. Okay? So if those two angles are congruent, okay, and this is going to be easier for me just to draw in instead of use GeoGebra. But you know that angle right there is now congruent to that angle right there, right? Is this angle here congruent to that angle there? And if the maroon triangle and the red triangle were the same, then doesn't that mean that all four of those blue angles are congruent? Does that make sense, everybody? Okay. So that's nice. That's useful. Okay. We have some information here that's going to lead us to our conclusion in a moment. The next thing I want to look at is not those isosceles triangles, but that isosceles triangle. Would you agree that that's an isosceles triangle? Would you agree that the one on the right, the white one, is also an isosceles triangle? Would you agree that those two triangles are congruent by side, side, side again? Okay. And would you be able to make similar arguments about maybe that angle right there being congruent to that angle right there? And can you say that angle right there is congruent to that angle right there? But because the red triangle and the white triangle were congruent to one another, could you say that all four of those red angles were congruent? Okay, so this is nice. We got a lot of congruencies here, right? Now, the reason we need all those congruencies is because I ultimately want to look at this top triangle or the bottom one. I just want to look at one of them, but it's got to be that one because that top triangle incorporates AB, the original segment we started with, right? And AB for that isosceles triangle right now, AB for that isosceles triangle is the what side? What was this special vocabulary word we said for the side that is incongruent to the other two? Start with a B. That's the base. AB is the base of that maroon or red isosceles triangle up top, right? Okay. And if you remember, there was a corollary, which again, just a theorem that is easily proven through the use of another theorem. Okay. That said, if that blue side, you guys can't really see it very well. I need a new projector. I'm going to. Is that better? You see that red segment better? Yeah. That red segment, C to E, okay? What does it do to angle ACB up top? It bisects it. If I look at this big angle up here, right? We just went through all the work looking at those congruent isosceles triangles and using the isosceles triangle theorem to show that basically these four red angles were all the same so that we could show that these two angles themselves are the same, so that we could then show that this red segment is an angle bisector of the vertex angle. Okay? And if you remember, we had a corollary that said if you have the angle bisector of the vertex angle, then it is always a what of the base? It's always a perpendicular bisector of the base. Okay? I think the way we wrote it in class was that that angle bisector of the vertex angle is perpendicular to the base at the base's midpoint. So that tells us E is a midpoint, which we've already verified that. But now it also tells us that this should be a right angle right there. Okay? And what's nice about this stuff, did we ever focus and try to force that thing to be a 90-degree angle? No, we dealt with circles and segments, right? That's all we did. Okay? But when we create those circles and those segments and the relationships that we did, we force a creation of isosceles triangles and congruent triangles, and that then provides us all the information that we need. Okay? So perpendicular bisectors exist because of what type of triangles? Careful. Just congruent. They might be right. Okay. Well, they exist because of congruent triangles. Okay. A lot of the things that we learn in this class, most of the things we learn in this class, are proven using congruent triangles. Okay. So that's the goal. If you are ever asked to prove a statement geometrically and you're not sure, I'm not saying this is going to work every single time, but if you're not sure what to do, you probably want to start with that. Okay. Because that works a lot of the time. Okay. Start with the idea of trying to show triangles congruent. Okay. So we're going to do a couple more of these. You can, if you guys want to save these things, I don't know if I said this yesterday in this class. If you want to save them, that's fine. I would save them to my, your geometry folder or whatever. Usually, I don't have any right now online for what we just did, but usually if we do a construction class, then I put that construction online as well on the website. So that is a perpendicular bisector, the construction of a perpendicular bisector. All right. Let's do, now that we have that, now that we know how to do that, that is actually the foundation. That is the process that we use to come up with a lot of other relationships of perpendicular lines. Okay, so the next thing I want you guys to do is just create a segment. Doesn't matter how big, doesn't matter its orientation, left, right, up, down, slope, whatever. But do it in a different GeoGebra. So either save that one and get out of it, or go up to File and click New Window, and that will open a blank tablet for you. If you click New, it's going to ask you to save, and if you do that, obviously you'll have it. If you hit Don't Save, it's just going to be like, you wrote a paper and you hit Don't Save, and you closed out and you didn't save your paper, right? Okay. But New Window just opens a new one over the top, and then eventually you'll close them all out. It's going to ask you to save all of them. So create that segment. Doesn't matter how big it is. Hey, we're going to take another point. Let's take your point tool, and I'm going to come over here, and I'm going to put my cursor on my line so that that hand shows up, and that tells me when I click the button that the point that I'm going to choose is actually going to be placed on that line. Okay. So I just colored mine so I can talk about it a little bit easier. That's going to be an important point for us. I want you to place it. Once you place it on the line, you can actually grab it, but you have to grab it with your arrow. You have to grab the cursor arrow. You can take it and you can start sliding it, move it anywhere you want to. Okay. It can't go past B obviously because there's nothing over there that exists over there. It can't go past A, but you can move it anywhere you want to on that segment. I want you to move it to somewhere that you are convinced that it's not the midpoint. Okay, so looking at mine, I know C is not the midpoint, right? Be fairly certain about that. We want to find a line that is perpendicular to AB, but now passes through C. Okay, so GeoGebra allows us to do this. If I don't do this, but if I click on here, there's a lot of lines that are perpendicular to AB. Would you guys agree with that? There's an infinite number of lines, but how many of them go through C? Just one. So we're going to see if we can find that one. All right. In doing that, it has the foundation of what we just did. Okay, of the proof that we just did, the construction that we just did. But we have to be able to get ourselves to that point first. Okay. So what we're going to do is we're going to look at this segment. And if you remember what we just did, we used the endpoint A and the endpoint B, right, to create the midpoint of our segment. Okay. Well, right now what we're doing, we're going to go through this point C. So we're going to try to figure out how can I force C to actually be a midpoint of some segment. Okay. So come up to your circle tool. Go down to circle the first one. Okay. The first one is again, kind of like if you had a compass in your hand, but now you're able to move that circle, move the size of that compass kind of freely before you start drawing. Okay. So I clicked on the point C, and I start moving my cursor away from C. And I want to click again, but I want to make sure that when I click a second time, that my circle is intersecting my segment 2 times. Okay. So your circle might be bigger or smaller than mine. Okay. You can come down like that. You can go. You can't do that because how many times does that circle intersect? Once. Okay. So I want to at least intersect my segment twice. So I'm going to go there. Okay. And now that creates a point D. Point D is really just an object that we can use to change and adjust that circle if we wanted to. So just hide D. I don't want this. I don't want the size of this circle to change. So we're going to hide D. All right. But okay, what we can do now is I can still move C around. And things are going to change. That circle is going to change, but it's still going to, when we move it, want to have the relationship that the circle intersects twice, okay? And that C is not the midpoint. Okay? But C is a midpoint. C is a midpoint of the segment that is in between this or inside this circle, isn't it? Okay. Now, what do you call? Let's do it this way. Let's ask it to find the intersection point of the circle and your segment. So it finds those 2 points, E and F. For a circle, what would you call that segment EF? And go. It's has endpoints on the circle, and it passes through the center of the circle. Would you guys learn that to be in like 7th, 8th grade, maybe before that? That's the diameter of the circle, right? Okay. And a diameter is always how big compared to the radius? Twice as big, right? Okay. So EC is a radius, CF is a radius. They're the same. So isn't C, by definition, a midpoint for that red segment? Does that make sense, everybody? Okay. So what we're going to do, let's hide the circle. Okay. And the only reason I had that circle is because I wanted to find those points E and F. Because now we're going to go back and do the exact same thing we did in the last construction. Let's start at E and start at F. Don't even worry about anything up there. That's blue now. Does that make sense? So I'm going to go to E, and we'll create a circle that is bigger than half of EF. Okay, so my circle tool, and it's this one here with the radius. I mean, that's probably the best one to choose. And we go E, and I'll choose a radius, maybe 5. Hit OK, and that's bigger than half of that red segment, right? Another way that you guys can do this is we can use that first one if I wanted to. Circle with center through a point. I can click on E, and now is it easy to see that that one there is going to be bigger than C? That makes sense? Okay, so I click Enter. Okay, and that gave me that circle. I think maybe I can't do this. Let's go. I create a congruent circle. Circle with center through a point. Circle with center and radius. Circle through 3 points. And I was thinking I could. That doesn't seem to be there. There is a way, but it doesn't seem to be the best approach. So we do want to use. I apologize. We do want to use this circle with radius. So again, click on E. Click something that you know is going to be bigger. If you've got if you choose a radius that doesn't go, to the right of C, doesn't pass over half of it, then just Control Z and then choose another circle a little bit bigger, and it might be a kind of a trial and error thing to get that circle. But now I'm going to go to F and do the same thing. So I use a radius of 5, right? Hit OK. And what do those two circles do? Intersect. Okay? And those two circles are congruent, right? So those two circles are congruent, provides basically isosceles triangles. It provides a bunch of congruent triangles. And it's going to provide then a segment or a line that we know to be perpendicular to the original blue line AB. Okay? And the proof of that is the exact same proof that we went through in that first question, our first example. Okay? So you're going to hit those intersect tools to get to define point G and point H, and then connect those. So what's nice then, I can obviously get rid of those circles. Okay? And you can be guaranteed, come back down here, click on the angle tool, click on G, C, and then either A or E, and it gives me a right angle, right? So I know for certain that segment is perpendicular to AB, and it passes through C, right? Okay. So using that circle, using relationships about diameters and radii, we force that C, that point that we're interested in, to be a midpoint of a smaller segment. Okay? And then we find the perpendicular bisector of that smaller segment. All right. So something we can do? We can then, your point C was a point that you can move, right? You can move that around. Okay? And then the red line should be, that vertical line that I have in there should be the perpendicular bisector every time. You see that 90, or not, it's just perpendicular, not a bisector. It's perpendicular every single time you see that 90 changes, right? Okay? But A to C is not the same thing as now C to B, right? So it's not a bisector, it's just perpendicular. Okay? So that is finding a perpendicular line through any point that is on the line. Okay? Let's do one more. So we either save that one, like I say, you save that one as a perpendicular line through a point on the line. And some of these constructions have lengthy names, okay? But those names model the properties that we should know about perpendicular lines. Through any point on a line, there is one and only one line that is perpendicular to it. Okay? Through that point perpendicular to the line. Let's click. Let's create a line here. Come up to your line tool. Make any line you want, and then hide the 2 points A and B that created that line. I just want the line. I don't want any extra points. Okay. Now go up to your point tool and click a point above your line. Not on your line, but above it. This is one of the main concepts that we've talked about in the last couple sections about how we measure things and how we measure distance. If I'm standing at C and I want to walk to that line, there's a lot of different routes I could take, right? And if I got 2, 3, 4, 5 different routes, I'm going to have 2, 3, 4, 5 different distances, correct? And actually, I have an infinite number of routes, so I have an infinite number of distances, correct? If you have an infinite number of objects, isn't one of those going to be the smallest? Okay, so we want to find the length or the distance from C to that line. Okay, and the way we do that is we find, how do we measure from a point to a line? What kind of lines do we use? What's the relation between the two lines? If I'm standing at C, how are you going to walk? We talked about this yesterday. This is where, kind of in my shoes, it gets kind of frustrating, guys, that if we talked about this yesterday, we measured that thing there, right? We also measured a point, or took a point and kind of measured, do it this way, we measured that angle there, correct? And we talked about how when this value here is the smallest, what is the relationship between the two lines? What's the angle going to be when that distance is the smallest? You see here that distance is 4.28, right? That angle is 84 or 85. Come over here, okay? We went to 4.25, and now we start going back up to 4.29, right? Well, yeah, we passed over that right angle. At the right angle is when that distance is going to be the smallest, okay? So we talked about that yesterday, and hopefully you understand as an instructor, when I ask questions like that we've talked about 3, 4, 5 times in the last couple of days, and it's just blank stares and nothing, that's frustrating, okay? So when we measure from a point to a line, we're going to use perpendicular lines to do that. So how can we create a line that we know from C is 100% perpendicular? And this is the way you do. You take a circle, okay? And you're going to, it can be a circle through with the center through a point. So that's the one that we can kind of change on our own, okay? And I want to make sure that my circle that I create around C intersects my line 2 times, okay? Now be intelligent about it. I want to have a little bit of room to work. I don't want to intersect like that because those 2 points are really close to one another. All right, so I'm going to give myself some room here, and I create that circle. Did that circle cross my line 2 times? Awesome. So when it crosses my line 2 times, we should have those 2 intersection points, right? Okay. Now, when I have those 2 intersection points, that's all I needed that circle for. So let's hide the circle. And we'll hide that point D, which was on the circle. Okay. Now, think in your mind, C to E would be a what of that circle that I just hid? It's a radius, right? C to F is a what of that circle I just hid? A radius. So triangle ECF up there is what type of triangle? Isosceles, right? And if I have an isosceles triangle, is there always a vertex angle? An angle C in this case is going to be that vertex angle, right? And is there always going to be a line that is going to bisect that vertex angle? And if we can find a line that bisects that vertex angle, that line is going to be perpendicular to the original line we started with, right? So what that kind of discussion is talking about, or what we're getting at here, is we're going to try to bisect segment EF. Find the midpoint of segment EF. Okay? So now this kind of delineates down to the first construction we did. Make your, or focus your attention just on EF, and we will find the midpoint of it. Okay? Once I find the midpoint of it, it's also going to provide me the perpendicular bisector. Okay? So I'm going to go at E, and I'm going to create a circle. So circle with radius. Click on E, and I don't know, 5 might work. I don't know. That looks like that's a little bit bigger than half, doesn't it? If it doesn't look that way to you, change it, make it bigger. But then I'm going to go to F and do the same thing. Hit OK. And it does tell me that they were bigger than half because they do intersect. You need them to intersect. Do those 3 points, all right, it's 2 points. If I look at the intersections, do those 2 points right there, G and H, do they look like they're collinear with C? Take your line tool. Take your line tool. Connect H and G. If I connect H and G, does that line fit itself through C? Okay. So I'm going to click and force that line to be there. And now when I hide those 2 circles, is that line there the perpendicular line that goes from C to the original line? Okay. Now, if you don't buy that, you don't think that's true, I'm going to find that intersection point there, I. And use my angle tool. And right there it tells me 270, so that angle is 270. How much should all 3 of these angles add up to? 360, so doesn't that have to make this one 90? Okay. I don't like this angle tool. I struggle with it all the time. So there we go. So that is 90 degrees. Okay. Now, why did I do that? Why was I interested in that? And we're going to see the use of this tomorrow inside a triangle. But I wanted to know not necessarily where this line was. Okay, we need to find that in order to determine from C to I. Make that blue. I want that segment because that segment right there, if I hide my line right there, and I'm going to hide the red segment just to eliminate some clutter here. Let's get rid of H. Let's get rid of G. That line right there is the shortest distance you would have to travel from C to your original line. Does that make sense? Okay. And we can guarantee, we can force ourselves to see this. If I click on the distance tool here and it says 4.25, now I'm going to change my rounding so you see it happen a little bit better. Okay. But if I walk from C to like J here, okay, and we ask it for that distance, we see that that's obviously bigger, right? Bigger than 4.247. Well, as I start to move J closer to I, that distance decreases, right? But it will never decrease. It'll never go below 4.24749 because once I get beyond that, what's it start doing again? Start going up. Okay? We are very interested in a lot of things that we do, construction-wise, engineering-wise. We're interested in that distance CI, the shortest distance from a point to a line. And that shortest distance is always found using perpendicular lines. Okay? You guys have seen this. If I have, hopefully you've seen this at some point in your life. Let's say that I have like a piece of plywood or something like that, and plywood comes in sheets that are 8 by 4, okay, 8 foot by 4 foot, and I want to cut this in half, right? Okay. When I want to cut this in half, I better measure over here 4 feet, right? Put a mark right there. Okay? I want to measure over here 4 feet. Put a mark right there, correct? Okay? What I do then is I take my, and actually, you know, some people might not even put a mark on both sides. Some people might just put that mark right there. Okay? Well, if I take my saw blade and I start cutting right there, okay, is that piece of plywood going to fit where I want it to go? No. Okay? So you take your straight edge, okay, and you make sure that it's a right angle right there. Okay? Because if it's a right angle right there with my straight edge, then it's going to be, because of parallel lines, it's also going to be a right angle over here, right? And that's going to be the shortest distance that I have to cut, and that then is going to make that thing a 4x4 square. And it's going to fit into the place that I need it to fit into. If I'm measuring a room, because I want to go buy tile at Lowe's and Menards, okay, or carpet or something like that, do I measure from, measuring length and width, right? Define area. Say this is the room I want to carpet. Okay? I measure from there to right there, right? Because that's the shortest distance from this point to the opposite line. I don't stand here with my tape measure here and then measure over there, because that distance is what? What is that compared to the width of the room? It's different. And in what way? It's longer. So if I use that as my width of my room, my area is going to be more than what it needs to be, right? And I'm going to go to Menards or Lowe's or whatever carpet store I'm going to, and I'm going to buy more stuff than I need, and that's wasteful, and it takes a hit on my bank account, right? So when you do that kind of stuff, there's a lot of geometry in the things that you're going to do beyond high school as a homeowner, as a parent, stuff like that, okay? You're going to use some of this stuff later on, all right? No homework this evening. Go to lunch.